Okay, so let's start with a video on our op-amp circuits. So starting straight away with a comparator circuit. So a comparator circuit in itself, all it does, it compares the voltage on the non-inverting input with the voltage on the inverting input, and then whichever one is going to be bigger, then that's where the output is going to be. So asks us for a suitable value of R. So the first thing that we want to do then is to work out what the voltage here we have on the inverting terminal, and then that's just a voltage divider. So therefore we've just here we've got 16 volts. Okay, so at the moment, we're going to get an output, a positive output for here. When the temperature, it says when the temperature goes above, we'll go 4 degrees. So when the temperature rises, so when the temperature goes up, the voltage just here is going to, the voltage there is going to go up. So we're going to get a positive output here. So we want when the voltage on the positive input is bigger than the voltage on the negative, voltage on the non-inverting terminal is bigger than the voltage on the inverting terminal. So that's going to be when we go past 16 volts. So we want V plus to be 16 volts or bigger. And then we can then just take it from there. So if the 16 volts across our resistor, therefore there must be 8 volts across our thermistor. So therefore we can work out the current through our thermistor. Current through our thermistor. So that's just going to be voltage divided by our resistance. So we're going to have 8 volts across the thermistor divided by the 3.2 kilo ohms that it says, equals 2.5 milliamps. Okay, so therefore then the voltage, across our the resistor, if we use the voltage across the resistor and the current going through it, then we can work out the resistance. So the resistance of R is voltage divided by current. So we're going to have 8 divided by, sorry, not 8. It's got 16 volts across it, hasn't it? 16 volts across it and 2.5 milliamps going through it. So 16 divided by 2.5 milliamps equals 6.4 kilo ohms. Okay. Explain how we can make an adjustment to the temperature at which the alarm is triggered. Well, there's two things that we could do. The most simplest one in the circuit is just to make that a variable resistor. What I could also do is alter the reference voltage here by altering one of those resistors or put a potentiometer in there, but it's obviously a lot more difficult for me to change. Okay, so right, let's move on now to some of our amplifier circuits away from our comparator. So first of all, we've got a gain of 100. So it's a positive gain, so I'm going to draw it the way that I draw my circuits. I find them obviously a lot simpler to see what's going on. And we've got our two resistors there. We've got feedback there like so, and RF and R1 output. 0 volts, and our input. So we know that gain for this circuit is 1 plus RF over R1, and so we've got, which is equal to 100, so RF over R1 equals 99. 99, there we go. So therefore, might as well just go for nice and easy values. So if we let R, because that's 99 to 1, so let R1 equals 1K, and therefore RF equals 99K. Okay. Right. Bandwidth of the amplifier. So I've obviously adapted this question slightly. So so bandwidth equals gain bandwidth product over the gain. So if we know what the gain is 100, if we stick with that, therefore gain bandwidth product equals bandwidth multiplied by gain. So we've got 15 times by 10 to the 3 times by 100 100 equals 1.5 times 10 to the 6, so that's megahertz. Okay. So what is the voltage gain of the amplifier at 15 kilohertz? Okay, so what we're going to do is think that we're going to have a response graph like this that is going to come along like that. So it's going to have a gain of 100, and then at 15 kilohertz, which is our bandwidth point, it will drop to 0.7 of our maximum. So V out at our bandwidth point equals 0.7 of our maximum. So therefore we're going to have 100 times by 0.7, which equals 70. 1 kilohertz signal is applied. What is the maximum amplitude that will avoid clipping distortion? So all we're effectively doing here is applying the formula gain equals V out divided by V in. Okay, so we know that we can get 12 volts out. We know that we've got a gain of 100, so we're looking to find out, well, what V in is. So V in is going to be 12 divided by 100, so it's going to give us 120 millivolts. What is the minimum slew rate? Okay, so we've got two formulas for slew rate. The one we're interested in is slew rate here equals 2 pi FVP. Now VP is the voltage peak on the output. So as I say, this is a slightly modified question there. So I'm only considering one amplifier. So we've got 1 millivolt going in with a gain of 100. Okay, so therefore our output equals 100 times 1 millivolt, which is 100 millivolts. The original question for this had a two-stage amplifier, so I would have to take that into account. So we've got 2 pi times by our 10 kilohertz, okay, times by our 100 millivolts. Times 10 to the minus 3. There we go. Which gives us as an answer of 6.28 times 10 to the 3 volts per second. Okay, that's a bit of a nonsense number, so we can turn that into terms of volts rather than kilovolts if you want to. So that would be 6.28 volts. So as we've come down by 1,000, therefore we can then change the units by 1,000. So then that would be milliseconds. Okay. Right, okay, so we've got an amplifier here that's got a variable gain. So the minimum gain that we're going to have is when that variable resistor is turned to 0. So I'm just going to have minus 2 over 2, which equals minus 1. The maximum gain is when we've got 56k on there plus the 2k equals 58k divided by 2 equals minus 29. Okay, then plotting that on our graph. Okay. So we're looking for a gain of minus 20. So we're told in the question here that it saturates at 18 volts. So the first thing I'm going to do is 18 volts divided by 20 equals 900 millivolts maximum input. Yep, so therefore I can then go on to here and look for where my 900 is. So there's 1 volt. So there is my oh, pen stopped working. Okay, so pen started working, so obviously what I did was identified where my 900 millivolts were. Okay, at 900 millivolts, identified where my 18 my 18 volts were, because I knew then that the output would then saturate, and then I've got a negative gradient line there. And if I want to, I can obviously check that if I put half a volt in, then I'm going to get 10 volts out, and I obviously can then check to make sure I do that, and obviously it can put an additional point in if I want to. But because I've done that, I've already actually got 2 points that will allow me to draw my gain line anyway, and it's allowed me to draw the saturation which occurs when they've got to maximum input. Okay, so we've got just two more. We've got another bandwidth response graph. So we're told here that our maximum, if we carry on from our maximum gain that we got was 20. So therefore, at the bandwidth point, we're going to have 0.7 of 20, which is going to be equal to 14. So, and at 24, so there is my 24. Okay. And I'm looking for 14 at that point. So there's 40. Looks like the pen's run out again of ink. There we go, 14. So coming along to there, at that point there, which I think is there. Eyesight not as good as it used to be. Let's zoom in a little bit. There we go. So and then I can then draw my line coming along at 20. And then at some point when I get close to that point, I can then curve it down through that point that dictates the bandwidth, and then making sure that I curve off at the bottom. Okay. Okay, so slew rate. So slew rate here. The other formula for slew rate equals the change in V out over delta T, the change in time. So on this one here, looking at our change in output, looking at what we've got here, then that line there is on 18 volts. So we've got a change from 0 to 18 volts. That's a change in 18 volts, and the time that it's taken is from 2 to 11. Okay, so 2 to 11. So that is 9 microseconds. Yes. So we've got 18 divided by 2 equals, it's going 9 volts per microsecond. Okay. This is a very important thing to do. People just instantly go for there as 11, and that's what they write as they write in here. But actually, we're starting off. It's at the point you're starting off, so that we've got to change over the 9 microseconds. Right. I decided not to do this one in the end because it's a repeat. So we've got one here. I just wanted to draw a graph. So if we've got here, we've got 80 millivolts going in. So we've got 80 millivolts times by 12 equals 960 millivolts. So therefore, drawing on a graph of suitable scale, 500 millivolts, 1 volt minus 500 millivolts minus 1 volt. We're looking to identify where, if that is 1 volt there, so therefore this one is going to be about 950. It's a non-inverting amplifier. So that is where that lines up with that peak there, starting off at 0 volts there, starting off there. At this point, we're at a peak here, which is also then when I get my minus 950 millivolts out. 1, 2, 3, 4, 5. There's 9, 6, 50, 60, somewhere like that, and so on and so forth. So I can't. So we can then just draw in what we've got here like so. I'll just do one more point for you. So somewhere there, here we go like so. Okay, so it's a non-inverting amplifier, so we're in phase, and at the moment then we're 12 times bigger. Right, okay, so summing amplifier. So summing amplifier here. So we should all be able to draw a basic summing amplifier. Summing amplifier is based on an inverting amplifier. Okay, so it's a 2-input summing amplifier. So I'm drawing it something like so. Okay, and then we're going to have V1, V2, and there is our output, and there is our input. Now what it's actually saying is, and if we take V1 as 0.1 of a volt and V2 is at 0.2 of a volt, we want to have 5 volts as our output. Okay, so how do we then tackle that? Well, in this, I would tackle this in the simplest way possible, because we're going to multiply these two voltages by a particular amount and then add them up. So instantly I certainly saw, and there are probably several ways of doing it, that if I take V1 and multiplied by that by 10, and then add that to V2 and I multiply that by 20, so 10 times 0.1 equals 1 volt, 20 times 0.2 equals 4 volts, so that equals to give me, that actually only gives me, that will actually give me minus 5 volts out, won't it? So how do I change that minus 5 volts out into a plus voltage out? Well, actually I do need to then to modify this circuit slightly on here, because what I need to then effectively do is to put another inverting amplifier in here that will then convert the minus 5 volts that I've got there into plus 5 volts there. And this, I say, we try and keep this as simple as possible. So the easiest way to do this is to have a gain of minus 1. So I can make that 1k and 1k, 10k, or whatever you want it to be. So now I've got plus 5 volts out by just doing by putting an inverting amplifier to do that. If you want this expressed in another way, for this first half of this circuit, so this part here, then effectively what we've got is minus V out is equal to 10 times V1 plus 20 times V2. So you could have it, you could be asked that to produce that type of circuit. So V2 has got the most gain. The V2 has got the most gain, so therefore R2 there, this is R2, R1 and RF that we've got. So R2 is going to be our smallest value from that. So as the smallest value is going to be 1k, we're going to let R2 equal 1k, which means that then RF is going to be equal to 20 times by the R2, which is going to equal 20k. Okay. So that's those two values. Now we know that we can slot those values in for calculating R1. We've got a gain of 10, well minus 10 technically, is equal to 20k over R1. So slotting in the values there, we can then see, it's not an equal sign, is it? See that R1 then is just going to equal 2k, and that is it.